So in this section 4.3, we're going to be working with vectors in the plane, and we're going to be looking at working with vectors as directed line segments, writing the component forms of vectors, performing basic vector operations, writing vectors as linear combinations of unit vectors, finding direction angles of vectors, and then using vectors to model and solve real-life problems. So these have a lot of relationships to both linear algebra and to physics. And let's go ahead and take a look at how we work with vectors. So when we're talking about directed line segments, now we're talking about directionality. So you see all of these vectors are moving upwards and to the right, right? If they moved upwards to the left or downwards to the left or downwards to the right, those would be different than these vectors. But these are all equivalent vectors because they have the same directionality, meaning the same slope. They're all moving in the same direction, and they're all the same length. So when we're talking about vectors, we're going to be talking about magnitude is the concept of length, and the concept of direction is going to be very closely related to the slope. Okay, so if we wanted to go ahead and take a look at how can we tell if vectors are equivalent, the first thing we'd want to check is we'd want to check the slopes. So the slope of vector v would be the change in y, 3 minus 2, over the change in x, 5 minus 2, which would be 1/3. All right, if I want to take a look at the slope of vector u, it would be the change in y, 1 minus 0, over the change in x, 3 minus 0, which is 1/3. Okay, so their slopes are the same. Now let's check their magnitude. So we denote magnitude by, it looks a lot like a absolute value, but the lines are doubled. Okay, so the the magnitude of v can be found using the distance formula. So we're really just finding the lengths. These are things you already know how to do. It's going to be 3 minus 2 squared plus 5 minus 2 squared, which is going to be the square root of 1 squared plus 3 squared, which is root 10. And if we take a look at the magnitude of u, that's going to be the square root of 3 minus 0 squared and 1 minus 0 squared. That's also the square root of 10. So these are indeed equivalent because they have the same slopes and the same magnitude, right? And you see they're both moving in the same direction. If we were moving from Q to P, now you notice also in terms of linear algebra, you had freedom to choose which was point 1 and which was point 2. R is point 1 and S is point 2. There's no choice about this, right? Because of the direction. It starts here and it goes there. So we would know it would be different if it was headed in the other direction. That would be the first thing probably we would check, right? But same slope, same magnitude, same general direction, then we know that they are equivalent. All right, if you want to take a look at the component form of a vector, we're going to be looking at, we've got an initial point P, and so you got P1 and P2, the two coordinates, or you could think of this as Px and Py, and then a terminal point Q, so the x-coordinate and the y-coordinate, and you can see we find the difference of the coordinates, and that becomes the component form, right? And then again we use the distance formula to find the magnitude. If the magnitude is 1, then it's a unit vector, and we'll talk more about unit vectors later. Okay, so if I want to find the component form, I'm going to find, right, an initial point here and a terminal point there. So I'm going to find the component form of vector v would be the terminal point x-coordinate minus the initial point's x-coordinate and the terminal point's y-coordinate minus the initial point's y-coordinate. And when I simplify that, I'm going to have -5, 6. And then when you do component form, you're talking about we changed the way the brackets look, so I should have actually done that up here. So the brackets become angle brackets as opposed to curved parentheses. Okay, and if I want to find the magnitude now, my magnitude of v will be found using the distance formula. So it's going to be, right, this is the difference of the x-coordinates, and this is the difference of the y-coordinates. So it's going to be negative 5 squared plus 6 squared. 25 and 36 is root 61. Okay, so component form, magnitude. Right, when we start talking about vector addition and scalar multiplication, so you'd have to go back probably to matrix operations to remember multiplying by a scalar, but it's basically like a coefficient. And you'll notice when you multiply by a scalar, it simply distributes into the coordinates. Okay, so I would take the scalar and I'd multiply it times the x and the y coordinate, and then I would get the new vector. Okay, and when we talk about adding vectors, we add the x's and we add the y's. So it's pretty straightforward stuff. If I want to do u plus v, that's going to be 1 plus 3 and 4 plus 2. So that's going to be 4, 6. Right, we want to subtract. Now, order's certainly going to matter now. U minus v, that's going to be 1 minus 3 and 4 minus 2. So that would be negative 2, 2. And then when we work with a scalar, that's going to be 2 times 1, 4, minus 3, times 3, 2. So that's going to be 2, 8, minus 9, 6, which is going to be 2 minus 9, 8 minus 6, which is going to be negative 7, 2. Okay, so pretty easy stuff. And you're basically doing what's relatively intuitive in terms of adding these things together. Okay, so we have properties of addition and multiplication. You'll notice they're the same as the properties you've seen before, right? So you've got commutative property, you've got distributive property, you've got all sorts of different properties around here, right? But these are all properties that we're pretty familiar with, and you're basically reestablishing that all of these properties still apply when you're doing vector addition and scalar multiplication. Okay, when we start talking about unit vectors, a unit vector is a vector with a magnitude of 1. So this item j is a unit vector, and this item I is a unit vector. And you can tell that we can also go into doing some other operations with these unit vectors. We'll be talking about those in a minute. So if I want to find a unit vector u in a specific direction, then I have to verify that it has a magnitude of 1. So one of the things we're going to need to work on is we know that the unit vector u would be equal to vector v divided by the magnitude of v. Okay, which also could be rewritten to be 1 over the magnitude times the vector in component form. Okay, so if we want to take a look at this, how do we do this? I know that my unit vector u is going to be equal to the component form of the vector, 6, negative 1, over the magnitude of that, which is going to be the square root of, excuse me, I don't need to write the vertical lines anymore, the square root of 6 squared plus negative 1 squared. which is going to be 6 negative 1 over root 37, and we would actually distribute the division, right? If what's a little confusing when you look at it like this, and maybe less confusing when you look at it like this, you can see now that 1 over root 37 is a scalar. It's harder to see that it's a scalar here. All right, so it's going to be 6 over root 37 negative 1 over root 37. And that's my unit vector. Now they want me to verify that the result has a magnitude of 1. If I want to do the magnitude of u, it's going to be the square root of 6 over root 37 squared plus negative 1 over root 37 squared. This is going to be 36 over 37, and this is 1 over 37. So the square root of 37 over 37, that's the square root of 1, is equal to 1. So that was my goal, is to verify that was the unit vector. It's a vector with a magnitude of 1. Okay, if we want to find a vector that has a specific magnitude and a certain directionality, we can do that as well. So what we know is that my vector w will be equal to the magnitude of the vector times 1 over the magnitude of my other vector times that vector, which is what we just did, right? So it's going to be 6 times the unit vector. So I've got, this is the formula for the unit vector. This is the magnitude I have to do, right? The unit vector will have a magnitude of 1 going in this direction. And when I multiply 6 times a unit with a magnitude of 1, I'm going to get a magnitude of 6. That's the idea behind this, right? So if I go ahead and put these items in, I'm going to be 1 over the square root of 2 squared plus negative 4 squared times 2 negative 4. So when I go through this is going to be 1 over 4 plus 16, that's going to be root 20, times 2 negative 4. Right, now I could multiply the scalar times this other scalar because I have 2 scalars now. Right, and I also want to simplify root 20 to be 2 root 5. And I'll have 6 over that, and the 6 and the 2 will cancel, leaving 3. So 3 over root 5 times 2 negative 4 will give me 6 over root 5 negative 12 over root 5. And this is component form of a vector with a magnitude of 6 that's moving in the same direction as this other vector. So remember, the steps we did is we found the unit vector of this vector by using this form, and then we multiplied it by 6 to find a new vector with the magnitude of 6 moving in that same direction. Okay, so when we write out our vector in this form with coefficients, the scalars v1 and v2 are horizontal and vertical components of the vector, because a vector moving in a certain direction, right, has a horizontal change and a vertical change. We would also call that slope, right? If you go back to linear algebra, if this was a coefficient times x plus a coefficient times y, the slope is going to be made out of the ratio of those 2 coefficients. So this is pretty familiar. So if I want to do a linear combination, which means this is a linear combination here, of this vector with an initial point and a terminal side, then what I can do is I can go ahead and find the component form right? So if the first thing I want to do is I want to find the component form of u. So that's going to be the terminal side minus the initial side, each coefficient or component. And when we get this, I'm going to have -6, -3. And all I have to do to put this in linear combination form is I have -6i plus, or actually in this case minus because it's negative, minus 3j. So component form, linear combination form. And you notice all that really happened is I added the I and the j, which represent horizontal and vertical change. So now again, now we've got items, right? We've done these items in component form. We've done addition in component form and subtraction. Now we're going to do it in linear combination form. So, but it's still basically the same. I want to have 5u, so I'll have 5 times I minus 2j, minus 2 times v, which is -3i plus 2j. I'm going to distribute the coefficients, 5i minus 10j, minus -6i plus 4j. So I've left the parentheses on. And now I'm going to distribute the subtraction, or the -1, if you want to think of it that way. So it'll be plus 6i minus 4j. And then I combine like terms. 5 and 6 is 11i. Minus 10 minus 4 is minus 14j. And there's my new form. If we want to find direction angles, when I know the terminal side, right? If u is a unit vector, right, which is going to determine the, right? So we're back to like the unit circle, right? It's a unit vector, so this is a vector with a magnitude of 1. That's making a circle with a radius of 1, just like the unit circle. We've got these that we already learned that this value y is sine, and this value x is the cosine. So these components of the unit vector can also be used to find sine and cosine. Okay, and this also will then allow me to find what angle creates the direction of my vector. Okay, so for supposing u is a unit vector, I can go ahead and use these formulas. Right here we find the magnitude times the sine and the cosine. We distribute the scalar, and we can go ahead and work this all out. But what we end up finding is that the easier way to go about this is that tangent's going to be sine over cosine. Now you notice that sine ends up being b and cosine ends up being a. So from this form that we already had, this linear combination form, we can pull out the sine and the cosine, find tangent, and then identify our angle. And that's a lot easier. So if I want to find the direction angle, I know that in this case tangent of theta will be 6 over -6. That's -1. And where is tangent -1? Well, tangent is -1 when we're at the 45s, right? We know that you'll get 1 or -1 for tangent on all the 45s. But here the x and the y would be positive. Here the x and the y would be negative. Those would be positive tangents. So up here would be where it would be negative. So that would be 90 degrees plus 45 degrees is 135 degrees. If we're working with this guy here, we'll have tangent of theta is equal to -4 over -7. That's 4/7. if I go ahead and go to my calculator, I don't see that as a standard angle. So if I do 4 divided by 7 equals, and then I do second tangent, I'm at 29.75 degrees. Okay, now if we think about where sine and cosine are negative, that's down here as we mentioned. So this 29.75 degrees, that's this reference angle. So it's going to be plus 180.7590, 209.75 degrees. Okay, some applications which are essentially going to be word problems. We're going to be working with this problem where we want to find the component form of a vector that represents the velocity of an airplane. The airplane is descending at speed of 150 miles per hour. That's the magnitude of my vector, at an angle 20 degrees below the horizontal. So this is 20 degrees below the horizontal. But that means that the angle we're working with is 200 degrees. So in working on this problem, if I go back to the formula we had before, that the vector would be equal to the magnitude of the vector times the component form, which would be cosine theta sine theta, which could also be simplified to be the magnitude times the linear combination form, which would be cosine theta I plus sine theta j. Okay, so if we're going to start with working with that, and we know what the magnitude is. The magnitude is 150 miles per hour. We know the angle is 200 degrees. So I'm going to have 150 times the cosine of 200 degrees plus 150 I plus 150 times the sine of 200 degrees j. Sorry, I ran out of room there. Actually, let me fix this. Let's move this over. There. 200 degrees j. And when I go ahead and find what cosine of 200 is, so if I put in 200 cosine times 150, that's negative 140.96 I plus 200 sine times 150, 51.3, negative 51.30 j. And then we can go from the linear combination form to the component form by just taking the coefficients. And here's our component form. Oops, sorry. There we go. If we want to work on this problem, we want to determine the weight of a boat and trailer. It takes a force of 600 pounds to pull the boat and trailer up a ramp inclined at 15 degrees from horizontal. And we want to find the combined weight of the boat and trailer. So now we've got this other information here. You can see that the force of gravity here is BA. So the vector BA, that's the force of gravity. Right? It's driving straight down through the boat. Now, when you look at the force that the boat is exerting versus the ramp, that's this other vector. It's perpendicular to the incline of the ramp, so that's BC. So really we should be talking about the magnitude of those guys. That's going to equal force on the ramp. And then if you think of this area here, this AC, the magnitude of AC, that's the force it's going to take to overcome the gravity and move it up the ramp. So that's our force to move. Okay, so what we want to do is we want to find the combined weight of the boat and the trailer. So if we go back to these guys, we know that, right, when you talk about this angle here, sine, right, the sine of 15 degrees looking at this angle is going to be opposite over hypotenuse, right? So I know that the sine of 15 degrees will be equal to, so remember what we're looking for is this force on the ramp. We want to find the magnitude of, the gravity. We want to find the magnitude of BA. Right? So then we're going to have the magnitude of AC divided by the magnitude of BA. Okay, well, we know what the magnitude of AC is. The force that's necessary is 600 pounds. So that's going to be 600 pounds divided by the magnitude of BA. So now I can find the sine of 15, but what I'm looking for is the magnitude of BA. So if I multiply both sides by the magnitude of BA and divide both sides by the sine of 15, then I'll be able to find my value. So if I take 600 divided by 15 sine, it's going to be 2,318 pounds essentially. So that's the weight, right? The weight is, of course, the force of gravity and the weight going through the ramp. Okay, so that's how I went ahead and solved that problem. So the last problem we're going to do is we're going to be working with this airplane traveling at a speed of 500 miles per hour with a bearing of 330 degrees. Right? And what this becomes a little confusing is the difference between the concept of bearing and the way we normally measure angles. So what you have to remember is that bearing are measured from north. This would be north. And it's measured clockwise, which is the opposite way. So if I have a bearing of 330 degrees, that's the 330 degrees. Right? What does that leave left here? It's another 30 degrees. So the angle we're talking about is 90 plus 30. It's 120 degrees. So that's where this 120 degrees comes from. Right? The book doesn't exactly, or this image doesn't explain that really well. Okay, and we're going to talk about bearing a couple times here. So what we've got then is we've got this airplane's traveling at a speed of 500 miles per hour. So I know then that the magnitude of my vector V1 is 500. Okay, it's on a bearing there. Negligible wind velocity. When the airplane reaches a certain point, it encounters a wind with a velocity of 70 miles per hour. Right? This new V sub 1, 70 miles per hour. I'm going to call that V sub 2, the magnitude of V sub 2. they called this v sub 1 and v sub 1, that's a little crazy, is 70. Okay, and what we want to find out is how does that change the speed and the direction of the airplane. So now if I want to go ahead and find the component forms of my two different vectors, I can go ahead and use the formula we've used before. So I know that my vector will be equal to the magnitude of the vector times cosine of the angle, sine of the angle. And that gives me a component form of negative 250 and 250 times radical 3 here. And when I find the component of this vector, component form of this vector, it's going to be 70. And it was 45 degrees over here, so we're going to be using 45 degrees as our angle. So 70 times cosine 45 degrees, sine 45 degrees, and of course those are both the same value. So I end up with, 35 radical 2, 35 radical 2, because this was 70 times radical 2 over 2 in each case. Then if I want to combine the vectors, my new vector, combining the two, can be found by adding them together. And remember, when I add my vectors, right, v1 plus v2, when I add my vectors, I'm going to add their component elements. So that's going to be negative 200.5. And converting these into decimals and adding them together, I'm going to get 482.5. Okay, great. Now, if I want to go ahead and find the angle involved, remember, we're going to go back and combine other things we've done before. So tangent would be sine over cosine, and if you remember, sine is going to be this component here, 482.5, negative 200.5. So I'm going to get negative 2.4065. And when I do second tangent to find this value, I'm going to get 67.4 degrees. Now, remember, that's a reference angle. So if I just want to know the angle, 67.4, that's this angle here, right? It's going to be 180 minus that. So 180 degrees minus 67.4 degrees is going to equal 112.6 degrees. And that's the angle that we have here, right? So it was 120 degrees, but the force of the wind has pushed it back to 112.6 degrees. But they also then want me to get the speed and the direction of the airplane. So if we look at the direction of the airplane, it's going to be found measuring from north, right? So this is going to be 270 degrees plus the reference angle. So the direction will be 270 degrees plus 67.4 degrees. And that's going to be 337.4 degrees. And finally, if I want to find the resulting speed, it's going to be the magnitude of my new vector, right? So the magnitude of v, again, I'm going to use the distance formula. So it's going to be negative 200.5 squared plus 482.5 squared, and the square root of that, which is 522.5 miles per hour. So summing it all up, we went through all of these different items. We went through how to represent the vector as a directed line segment, how to write in component form. We did vector addition and scalar multiplication. We wrote vectors as linear combination of unit vectors. We went ahead and found direction angles of vectors, and we did a couple of real-life situations. So that's your overview of vectors.